Okay, so thank you for giving me the great opportunity to talk here. So first, I'm today my
The screen is not in full screen mode.
Connection is
Okay,
unstable. Will be unstable. No,
no.
really?
Now yes.
Okay.
Now
it will. Yeah. Okay. Now it's
now
good.
Yes. Okay.
Good.
So okay. Okay. So today I would like to talk about this. That's right. Just a moment. Okay. Today I would like to talk about this publication in Physical Review B. There is a large variety of superconductors, as you know, in nature and affinity synchronized. For instance, unconventional superconductivity and topological one with orbital degrees of freedom and inversion symmetry breaking has been reported in iron-based superconductors and so on. To unveil the possibility of topological superconductivity caused by the orbital degrees of freedom in our study, we focus on the oxide interfaces with two remainder electron gas. However, our theory is general and it can apply to a large class of materials where orbital degrees of freedom are relevant and inversion symmetry is broken. Oxide interfaces such as area or STO has a two-dimensional electron gas with T2G electron degrees of freedom in the presence of spin-orbital coupling and thus very good candidate for studying multi-orbital non-central symmetric superconductors. This is the motivation and purpose. Our motivation is the topological superconductor and spin-orbital coupling. Here, we propose the topological superconductivity in the three orbital non-central symmetric superconductors by focusing on the interorbital isotropic pairing symmetries. Then, we solve the multi-orbital gap equation to find the favorable pairings and investigate these bulk and edge states. Model Hamiltonian is based on the T2D electrons in 2D with inversion symmetry breaking due to the lack of horizontal mirror. This Hamiltonian is constructed by the three terms like this. The first one is the kinetic energy term. dxy orbital has the isotropic hopping, and dyz and dx orbitals have the quasi-one-dimensional intra-orbital hopping like this. The second one is the atomic spin-orbital coupling term, and the third one is the inversion symmetry breaking term, so-called orbital Rashba coupling. In our study, we focus on the local pairing like this. In the single orbital model, spin singlet S-wave pairing is allowed, but the spin triplet S-wave one is not allowed because of the Fermi-Dirac statistics. However, in the presence of orbital degrees of freedom, we can distinguish the orbital and the momentum k in the pair potential. Then, spin triplet orbital singlet S-wave states can be allowed. We cannot focus on this in orbital dependent spin triplet states in the single orbital model. For this reason, Professor Maino, who found strontium-deuterium superconductor in 1994, called this orbital dependent spin triplet pairing beyond the traditional and then conventional superconductivity. In this study, we focus on the spin interorbital spin triplet orbital singlet S-wave pairing. To investigate the available interorbital pairing near the critical temperature, we introduce a linearized irreducible equation. This equation is difficult to be solved, so we adopt the mean field and weak coupling approximations. For these approximations, we can obtain the multi-orbital gap equations like this. Because this equation, we compute the maximum eigenvalue and the corresponding eigenstate that gives the most favorable pairing configurations. pairing symmetry must obey the irreducible representation of a point group. Oxide interfaces that we focus on belongs to the C4V point group, and this C4V point group has a 5 irreducible representation A1, A2, B1, B2, and E. So we will investigate which irreducible representation for interorbital pairings can be stabilized for the chemical potential and ratio of interorbital attractive channels Vg and Vxy. In our calculation, interorbital A1 and B1 representations with spin triplet orbital singlet S-wave are stabilized. Brown line is the boundary between A1 and B1 pairings, and it depends on the number of Fermi surfaces and the different color regimes. Especially interorbital B1 pairings is stable for the large chemical potential and Vxy pairing interactions. In this talk, we focus on the interorbital B1 representation. This is a schematic illustration of the Cooper pair in interorbital B1 pairing with spin triplet orbital singlet S-wave. For the spin triplet state, this interorbital B1 pairing is described by the spin d vector like this. In the bulk, nodal points topological protected by the chiral symmetry of BDG Hamiltonian appear in the diagonal direction. These nodal points have a non-zero winding number +1 red and -1 blue one. To investigate the edge state, we calculate the surface density of states. For the nodal point, when we make the 110 oriented surface, zero energy flat band appears around like this. Sorry, I'm sorry. Or even if the width of the zero energy flat band is short. As a result, zero energy peak of the surface density of states also occurs like this. Blue line is the surface density of states at 110 oriented surface. The black one is the bulk density of states. These are the edge of states for topological superconductivity. So we demonstrate that the interorbital B1 pairing leads to an interorbital topological superconducting state. Finally, summary and conclusion. We show the topological superconductivity in multi-orbital non-central symmetric superconductors, such as oxide interfaces, can be achieved. We found that interorbital B1 representations with spin triplet orbital singlet S-wave electron pairing, spin orbital coupling, and pairing interaction. Spin triplet S-wave B1 pairing provides the interorbital topological superconductivity beyond the conventional and unconventional superconductivities. So finally, I would like to show our collaborators. These are the collaborators in this study. This collaboration is supported within the quantitative program OSS International. Thank you for your attention.
Okay, thank you very much, Yuri, for your nice talk. And now we have time for a couple of questions. There is already one from David. Please, go on.
Yes. Do you have a speculation of how this spin triplet orbital singlet order parameter would be affected by impurities?
That is a good question. This is so impurity is instabilities is I think that I am thinking of that we should check the impurities instabilities for this pairing symmetry, but I believe that this pairing symmetry would be stable because of the local pairing. That is independent K or independent momentum pairing.
Right, thank you.
Yes, you're welcome.
Okay, thank you. And there is another question by Victoria, please.
Yeah, maybe you have told. Do you consider only S-wave pairing or something else? If yes, then why
Yes.
only S-wave pairing? Why
So
only?
this because S-wave pairing is the most simple case, but I think that this parity dependence, so we can apply to the D wave and G wave, another given parity pairing. But then, so so we can also consider the interorbital D wave pairing, but in this study, we've just focused on the most simple case. This is S-wave case.
Okay, thank you very much.
But as you told, okay, you're welcome.
No, but I understand. My supervisor always was saying that we look under the lamp, not somewhere else.
Yeah, exactly. Yeah, we can apply to the D wave case. Yeah, exactly. Yeah.
Yeah, thank you very much.
Okay, then thank you very much, Yuri.
Sorry, I am.
Yeah, and now it's